All right, let's get into it. Have you ever stopped to think about how the data that runs our entire world actually gets from one place to another? Today we're going to pull back the curtain on one of the most basic, yet most important processes in all of modern technology.
So let's start with the big question. We all know everything is just ones and zeros, right? Binary data. But that data can't just magically teleport across the planet. It needs a physical form. So how in the world does an abstract concept like a 1 or a 0 become something real? Something that can actually travel through a copper wire, a fiber optic cable, or just the air all around us?
Here's how we're going to break it down. We'll start with the data itself, then learn the physical language it has to speak. We'll see how a full message gets written in that language, explore the dangers it faces on its trip, and finally, see how this one simple idea is the foundation for our entire connected world.
Okay, first up, setting the stage. We've got to build a bridge from the clean, perfect world of digital information to the messy, real world of physics and electronics.
And I mean everything. It doesn't matter if it's a 4K video, an important work email, or just a simple text message. If you zoom in far enough, it's all just a gigantic list of ones and zeros. That's our starting point, this long abstract sequence that needs to go somewhere.
So how do we give those bits a physical body? Well, we have to translate them into a language that electronic circuits can actually speak and send, and that is the language of pulses.
The most basic letter in this new alphabet is something called a pulse. You can just think of it as a tiny, super fast event, a quick spike in voltage or a quick dip. It's a simple physical action that we can easily create on one end and, this is the important part, we can detect on the other.
And the translation from bit to pulse can be beautifully simple. A really common way to do it is to just map one to the other directly. If you want to send a 1, you send a quick pulse of positive voltage. If you want to send a 0, you send a pulse of negative voltage. It's a one-to-one translation. A binary choice gets a binary physical state. Simple as that.
All right, so we've got our letters, our positive and negative pulses. Now it's time to string them together and actually write a message.
Let's just walk through a quick example. Say our system needs to send the sequence 1011. It reads the first bit, it's a 1, boom, it sends out a positive pulse. Next up is a 0, okay, out goes a negative pulse. Then it sees 2 ones in a row, so it sends 2 positive pulses, back to back. What you end up with is this flowing electrical waveform that is the actual physical version of our binary data.
And believe it or not, you now know what pulse modulation is. That's the name for this whole process. It's the act of modulating or changing a series of pulses to embed information in them. This is the exact moment our abstract bits become a real, physical signal ready to start its journey.
But, just like any epic journey, this one is not without its dangers. The signal has to travel through some kind of physical medium, a communication channel, and that path is almost never perfect. And when we say communication channel, we just mean the stuff the signal travels through. That could be the copper in your Ethernet cable, the super pure glass in a fiber optic line, the air itself for your Wi-Fi, or even the magnetic coating on a hard drive platter. They all act as a channel.
Now, when we send our signal out, it's perfect. It's a beautiful, clean, rectangular pulse. The edges are sharp, the voltage level is unmistakable. This is our ideal message exactly as we intended it.
But by the time it gets to the other end, well, it can look a lot more like this. It's been smeared out, the sharp edges are all rounded off, it's distorted. The physical channel has essentially chewed it up a bit, changing the shape of our perfect pulse along the way.
The source material we're looking at puts it perfectly. It says these pulses get so smeared out that they're no longer distinct from one another. They actually start to bleed into each other, to overlap. And that right there is the central challenge of all high-speed communication. This smearing effect has a name, and it's the main villain of our story today. Intersymbol interference, or ISI. It's when the energy, kind of like the ghosts of the pulse that just went by, spills over and interferes with the pulse we're trying to read right now. And that interference is what causes errors, making it hard to tell a 1 from a 0.
So we've got this huge, fundamental problem. But here's the thing. Understanding this problem, and more importantly, how we solve it, is the key to unlocking how pretty much all of our modern digital communication actually works.
And here is the absolute crucial takeaway. The faster you try to send your data, the more pulses you cram into every second, the worse that smearing, that ISI gets. So the entire game of making things faster is really just a constant escalating battle against intersymbol interference.
But we do fight back.
Modern receivers have these incredibly clever digital circuits called equalizers. Their whole job is to figure out exactly how the channel is messing up the signal and then apply the perfect opposite kind of distortion. It's kind of like noise-canceling headphones for data, and it cleans those smeared pulses right up, restoring them to their original shape.
And this fight is happening literally everywhere, all the time. We're talking about the massive fiber optic cables that run under the oceans, signals being beamed to satellites in space, the Wi-Fi router in your living room, your phone's connection to the cell tower. Every single one of these technologies is built around sending pulses and then winning the war against ISI.
In fact, for you to even be watching this right now, your device is performing this incredible dance of sending pulses, receiving distorted ones, and cleaning them up billions upon billions of times every single second. It is a constant, high-speed ballet of physics and information.
Which really, it leaves you with a pretty amazing thought. We've spent decades getting really, really good at beating intersymbol interference. But as our demand for data just continues to explode, you have to wonder, what new, stranger forms of interference are waiting out there for the next generation of engineers to discover and to conquer? Something to think about. Thanks for joining me.